Hey guys, welcome to lesson 7.3. Today we're going to talk about a new type of function called the logarithm, and we're specifically going to talk about it in terms of being an inverse of the exponential function. So let's go ahead and do a little introduction to the idea of what a logarithm is. So the way that I always love to introduce logarithms is I like to talk about exponents. So let's say, for example, we have 2 to the x is equal to 4, for example, right? Obviously, this is kind of new, right? Because we got to solve for x, but x is in the exponent, so we don't really know how we can solve that to get x by itself. So we kind of have to think to ourselves, well, what number could I plug in for x that's going to give me the result of 4? Now, this is obviously an easy example because we know that 2 to the second power would give us 4. So if we raise 2 squared, that would give us the final result of 4. So obviously, in this case, x would be equal to 2. But what happens if we have something a little bit more complicated like this? What if we had 2 to the power of x is equal to, 15? Well, obviously, there's no whole number that I could plug in for x up here that's going to give me 15 as an answer. Because obviously, if I plugged 1 in, 2 to the first power is just 2. We know that 2 to the second power is 4. 2 to the third power is going to be 8, and then 2 to the fourth power is 16. Nowhere in there did we get a result for 15. So we have to have some way of figuring out what x is equal to, and that is where the logarithm function comes in. So the logarithm, base b, of a positive number x is defined as log base b of x is equal to y if and only if b to the power of y is equal to x. So essentially, we use the logarithm function to figure out what the answer for the exponential variable is going to be. So what I could do is I could use the base of my exponent, plug that in as the base of my logarithm, and then I could plug in, well, whatever's on the right-hand side of the equation. So the answer, I could plug that into the logarithm as well. And then using the logarithm function, I'm going to figure out what the appropriate value is for my exponent of my base, okay? So you can read the logarithm as log base b of x. So if I say log base b, what that means is, so for example, if I said log base 3, that means that the base of my exponent, or the little number underneath the logarithm symbol, is going to be a 3. So I always say it as log base b of x. So in other words, the logarithm y is the exponent, and again, I already explained this before, but it's the exponent to which b must be raised to get x. So again, always refer back to this example. If I have a base raised to an exponent, and that is equal to 15, then I can just simply rearrange some stuff, put it into logarithm form, and I can evaluate what the appropriate exponent is to raise 2 to in order to get the answer of 15. So a logarithm function is the inverse of an exponential function. Okay, so when we're talking about inverse functions, logarithms essentially undo exponential functions. They're inverses of each other. Now, a logarithm that uses base 10 is known as the common log. So this is one of those things, right? When we talk about square roots, we know that the common index that we use for square roots is 2. So if you just see a root symbol without any number, you just assume that it's 2. Now for logarithms, that key number is going to be 10. So if you just see log of x, we assume that the base is 10. The only time that we're going to see a number down there is if the base is not 10. So for example, if we're talking about a base of 3 for an exponent, we're going to have to write log base 3 of x, right? So the number underneath the logarithm symbol is assumed to be 10 if we don't see any number down there. Now you can write log base 10 of y as log of y, and that's kind of what I just described above, is that those two are interchangeable because it's assumed to be 10 if you don't see a number. Finally, a logarithmic scale is any scale that uses the logarithm of a quantity instead of the quantity itself. So let's go ahead and talk a little bit about the characteristics of logarithm functions. So first of all, what is the parent function of a logarithm? Well, y equals log base b of x when b is greater than 0 and b does not equal 1. That is the parent function of a logarithm. Now let's talk about the stretch of a logarithm graph. So what happens if I'm looking at my graph, like what in my function is going to cause my graph to stretch? Well, let's say we have y equals a times log base b of x. If the absolute value of a is greater than 1, that's going to cause your graph to stretch. Now, what about a shrink? Well, same thing. If we have y equals a times log base b of x, but this time, if the absolute value of a is in between 1 and 0, or in other words, if it's a fraction, then that tells you that you're going to be looking at a shrink when you are putting the logarithm on a graph. Translations, again, we're looking at translations h, comma, k, so vertical translations and horizontal translations. So let's write down the formula here. Y equals log base b of x minus h plus k. This is going to represent the formula for your translations. We know that the stuff inside the parentheses, okay, the number that we're adding or subtracting to x, that's going to be our horizontal shift left or right. As always, we're thinking opposite. So for example, if we had x minus 3 inside the parentheses, we would be thinking, okay, we have minus 3. Typically that in our minds tells us we're going left, but we're thinking opposite. So if we have minus 3, that actually means we're going to go to the right 3 units, okay? So there's going to be a horizontal translation to the right for 3. And then the number on the outside that we're adding or subtracting, the plus k, that is how many times you're going up or down when you are translating your graph, okay? So all of the transformations combined is going to look like this formula, y equals a times log base b of x minus h plus k. This is all the possible transformations that you can make to the logarithm graph. Okay, let's go ahead and jump down to where it says write exponential equations in logarithmic form. This is going to be the most useful rule that we learned today because this actually tells you how to convert those exponential equations into logarithms, and then we can solve for the stuff in the exponent. So the definition, and this is going to be the rule that we use when we're converting from exponential form to logarithmic form. If x equals b to the power of y, then log base b of x is equal to y. So take a look and see what happened here from exponential form into logarithmic form. First of all, the base of the exponent is still the base of the logarithm. It goes underneath the logarithm symbol. Then the exponent goes on the other side of the equal sign, and that makes sense because we're trying to solve for the stuff in the exponent. And then the answer to whatever the exponential equation was, that is what we're plugging in right next to the logarithm symbol, okay? So we are evaluating the logarithm with this base, and then we're putting this number into the logarithm function. All right, so another way of thinking of this is when we have an exponent, we have our base, we're raising it to whatever our exponent is, and then we get an answer. So I have base to the exponent is equal to your answer, and I'm going to put answer in purple. Okay, so really what we're doing here is we're just, to convert this into logarithm form, we're just plugging stuff in where it's appropriate. So again, the base is going to go underneath the logarithm. So we have the log, and then we're going to put whatever our base is down below. And then instead of having our exponent right here, we have our answer that we're plugging into the logarithm function. So I'm going to plug in my answer. And that is equal to whatever the exponent was. And that makes total sense because, again, the whole point of the logarithm is to solve for the exponent. So we have log base answer is equal to whatever the exponent is. So either way you're looking at it, just remember this is how we're going to set it up. So we are going to write the following exponents in logarithmic form. Example number 1, we have 36 is equal to 6 squared. Well, first of all, your base here is 6. So I'm going to say, okay, here's my base. My base is 6. My exponent is 2. And my answer, which I made purple up there, is 36. So now we're just going to plug it all into the appropriate spot. So we have log base, and again, the base we're dealing with here is 6. So I have log base 6, and then I put the answer next to the logarithm. So log base 6 of 36 is equal to whatever my exponent is, which is 2. So logarithmic form would be log base 6 of 36 is equal to 2. Let's look at part B. We have 8 over 27 is equal to 2/3 raised to the power of 3. Once again, my base here is 2/3. My exponent is 3. And my answer is 8 over 27. So I'm literally just going to plug all of that stuff in where it's appropriate. So I have log base, well, my base here is 2/3, so I have log base 2/3 of whatever my answer is, 8 over 27, and that is equal to my exponent, which is 3. So I have log base 2/3 of 8 over 27 is equal to 3. Okay, last but not least, we have 1 equals 3 to the power of 0. Once again, we're going to put that into the logarithmic form. So I have log base, the base of my exponent is 3. So I put log base 3 of whatever the answer is, log base 3 of 1, and that is equal to my exponent, which is 0. And that, ladies and gentlemen, is how we convert exponents into logarithmic form. Just use the rules that we have up here and practice really hard, and it'll become second nature after a while. All right, let's go ahead and move on to the next piece. Okay, so now we're going to talk about how to actually evaluate these things. So example number 2, find the value of each logarithm. Now, these 3 examples are some more basic examples of what we're going to see when we're evaluating logarithms. And all 3 of these examples allow us to use a little trick that I'm going to teach you to evaluate the log. Now, I'm going to show you a ton of different ways to evaluate the logarithms, and there's a really specific rule that you can use, and it makes it easy to plug it into the calculator. But today I'm going to teach you the little trick, and as we get farther along with logarithms, you'll learn more ways to evaluate. So let's go ahead and look at part A first, log base 5 of 125. Now, using the little trick, the first thing I want to do is I want to put this in exponential form. Now, obviously, in order to do so, I need to have an equal sign, so I have 3 different parts to the logarithm, and then I could easily write it in exponential form. Since we're trying to evaluate it and we don't know what it is, I'm just going to assign log base 5 of 125, I'm going to set that equal to some variable p. Now I can easily put that in exponential form. I know that the base of the exponent is going to be 5. We know that logarithms evaluate the exponents, so the answer to the logarithm, whatever that is, that's going to be our exponent, and that is equal to the number in the middle, which is 125. Now, the trick that we're going to use is we're going to try to make both sides of the equation the same base. Because if we can create 2 situations, all right, with the same base, and we're setting them equal to each other, what we can do is we can set the exponents equal to each other. Okay, if we have the same base, then we can set the exponents equal to each other, and that's going to give us our answer for our logarithm. So obviously, 125 can be written as a base of 5 because we know that 5 to the 3rd power gives us 125. So instead of 125, I'm going to say 5 to the power of p is equal to 5 to the power of 3. Now we have a situation where we have the same base, we're setting them equal to each other. We have 5 to the power of p equals 5 to the power of 3. So what we can do is we can set the exponents equal to each other. So p, in this case, would have to equal 3. So log base 5 of 125 is equal to 3. Let's go ahead and move on to part B. Part B says log base 4 of 32. Okay, so once again, what we need to do is we need to, first of all, put this in exponential form. So I'm going to set this equal to p because we don't know what the logarithm represents yet. We don't know what it's equal to. Now I'm going to put this in exponential form. I have the base of the exponent, 4. We know that logarithms evaluate exponents. So my exponent is going to be p, which is equal to the number in the middle, 32. Now I want to write this in such a way so that we have the same base equal to each other so we can set the exponents equal. So this is a little tricky because 32 cannot be written as a base of 4. We know 4 to the 1st is equal to 4, 4 to the 2nd is equal to 16, but oof, 4 to the 3rd is equal to 64. So obviously we can't write 32 as a base of 4, but I can write 32 as a base of 2, as we know that 2 to the 5th power is going to give us 32. Also, I can write 4 as a base of 2 because 2 squared is going to give me 4. So let's go ahead and write both of these numbers with a base of 2. So instead of 4 to the power of p, I'm going to have 2 squared to the power of p is equal to, instead of 32, I'm going to say 2 to the power of 5. Now, obviously, we have a power raised to a power here, so I could rewrite that as 2 to the 2p, because again, if we have a power raised to a power, we multiply, and that is equal to 2 to the power of 5. So once again, I have the same base on either side of the equal sign, so what I can do is I can set the exponents equal. So I can say 2p is equal to 5. Okay, again, I'm taking these exponents, setting them equal to each other. And then I'm going to solve for p. Let's divide both sides by the 2. And we get p equals 5 over 2. So the logarithm base 4 of 32 is equal to 5 over 2. Last but not least, part C, we have log base 64 of 1 over 32. Once again, let's go ahead and set this equal to p, put it in exponential form. We're going to have the base 64 to the power, which is p, is equal to the middle 1 over 32. Okay, so once again, I need these to have the same base. Now, obviously, if I have a fraction here, this tells me that I'm going to have a negative exponent of some sort because negative exponents give me fractions. But let's go ahead and look at the numbers. We have 64 and 32. Now, I need to think about what base can I create out of both 32 and 64? Well, again, 32 is 2 to the power of 5. So let's think about whether or not we can make 64 a base of 2. And we do know that if we were to raise 2 to the 6th power, that would be 2 times 2 times 2 times 2 times 2 times 2, which would give you 2 times 2 times 2. That gives me 8 times, okay, 2 times 2 times 2, which gives me 8. And 8 times 8 does give me 64. So 2 to the power of 6 is something that we could rewrite 64 as. So I could say 2 to the power of 6 raised to the p is equal to 1 over 32 can be written as 2 to the power of 5. Now, once again, we know that if this is a positive exponent in the denominator, if I were to flip this up, it would just make the exponent negative. So I could say, well, obviously, 2 to the power of 6 to the power of p is 2 to the 6p is equal to, I could flip this exponent up, and that would give me 2 to the negative 5. So we have the same base on either side of the equal sign. Now I just need to set the exponents equal. So 6p equals negative 5. So if I say 6p equals negative 5, divide both sides by the 6, and we're going to get p equals negative 5 over 6. So the logarithm is negative 5 over 6. Once again, we are always trying to make the same base so that we can set the exponents equal to each other with these basic examples. Let's move down to a word problem because I know we've all been eagerly awaiting this word problem. Woo! So using a logarithmic scale, let's go ahead and do example number 3. The formula below compares the intensity levels of earthquakes where I is the intensity level determined on a seismograph and M is the magnitude on the Richter scale. So we have the formula that's given to us, log of I sub 1 over I sub 2 is equal to M sub 1 minus M sub 2. Let's go ahead and take a look at the information that we're given. So in 1995, an earthquake in Mexico registered 8.0 on the Richter scale. In 2001, an earthquake of magnitude 6.8 shook Washington state. How many times more intense was the 1995 earthquake than the 2001 earthquake? Now, what we can do is we can use this formula right here, and what I sub 1 over I sub 2 is going to evaluate is exactly what the question is asking. How many times more intense was the 1995 earthquake than the 2001 earthquake? So we know what M sub 1 and M sub 2 are, right? Because we're given what the magnitude is on the Richter scale. So M sub 1, I'm going to say that that's the magnitude of the first earthquake in Mexico, which was an 8.0. So M sub 1 is equal to 8. M sub 2 is going to represent the magnitude of the second earthquake, which was a 6.8 on the Richter scale. So M sub 2 equals 6.8. Now I'm just going to plug both of those things in, and I'm going to try to evaluate the stuff in the middle, I sub 1 over I sub 2. So let's use that formula. Log of I sub 1 over I sub 2 is equal to M1 minus M2. Well, I know that M1 is equal to 8, and then I'm subtracting M2, which is equal to 6.8. So I have log of I sub 1 over I sub 2 equals 8 minus 6.8. Obviously, I could simplify this a little bit, so I get log of I sub 1 over I sub 2 is equal to 8 minus 6.8, which gives me 1.2. Now I need to solve for the I sub 1 over I sub 2 in the middle. In order to do so though, I'm gonna have to put this in exponential form and not logarithm form, because obviously if I want this stuff to be by itself, I can easily just figure out what my base is, raise my base to this power, and then I sub 1 over I sub 2 is going to be isolated. Now, obviously, if we don't have a base written underneath the logarithm, like we said in the beginning, it's assumed that our base is 10. So I can use the base of 10 to put this in exponential form. So I'm going to have the base, which is 10, raised to the power, because logarithms evaluate powers, 1.2, is equal to I sub 1 over I sub 2. Okay, so now this is easy because I sub 1 over I sub 2 is isolated. All we have to do is raise 10 to the power of 1.2. And what this is going to give you is I sub 1 over I sub 2 is approximately 10 to the 1/2, or 1.2, excuse me, is going to give me 15.849. Okay, so since we have a word problem, we need to have a word answer. So what I'm going to say is, okay, well, therefore, since I sub 1 over I sub 2 is 15.849, the 1995 earthquake, so I'm going to say the 1995 quake was about, and I'm just going to round this up, was about 16 times stronger than the 2001 earthquake. So I'm going to say then the 2001 quake. Okay, so we figured out what I sub 1 over I sub 2 was, so that told us that it was about 16 times stronger than the 2001 quake. Really, the hardest part here is just recognizing that since we just had a logarithm, right, it's assumed that we have a base of 10, okay? Because we know that if we just see the log symbol, it's a base of 10. Once you figure that out, though, it's really a matter of just putting it in exponential form and then just plugging it into your calculator. Awesome. All right, let's go ahead and move on to the next page where we are going to explore the graphs of logarithm functions. So, example number 4, graph y equals log base 2 of x. Then we're going to describe the domain and range and identify the y-intercept and the asymptote. All right, so first of all, we recognize that we have all these x values that I'm going to plug into my function. My function is log base 2 of x. Now, the problem here is that if I plug, say, -2 into the logarithm function, I would have log base 2 of -2. And then you're like, well, how on the earth am I going to evaluate log base 2 of -2? I don't know how to do that. So what we're going to recognize here is that logarithm functions are inverses of exponential functions, like we said from the first page. So the inverse of log base 2 of x is 2 to the power of x. Those two functions are inverses of one another. Now, what do we know about inverses? If I find what the outcome is of an inverse, all I need to do to find the actual ordered pair of the real function is I need to switch the x and y values, as we know that the domain and the range of functions are flipped if we're talking about the inverse. So what we're going to do is we're going to evaluate all of these x values at the inverse. Then we're just going to simply flip the x and y values to give us all of the ordered pairs for the actual function. So let's go ahead and plug those x values into the inverse function first. So if I plug -2 into the inverse function, I'm going to get 2 to the power of -2. In order to make negative exponents positive, I got to flip the fraction bar. So this would give me 1 over 2 to the positive 2, or 1 over 4. For the second one, I'm going to plug in -1, so I have 2 to the -1. Once again, we're going to flip that fraction bar, giving us 1 over 2 to the first power. Then I have 2 raised to the 0 power. Anything raised to the 0 power is 1. Then I have 2 to the first power. That's going to give me 2. And last but not least, 2 to the second power gives me 4. Now, in order to find the ordered pairs of the actual function, all I'm going to do is I'm going to flip my x and y values, because the outcomes of the inverse are going to become the inputs of the actual function, because I'm just switching the domain and range. So my first ordered pair for the actual function is going to be 1/4 comma -2, 1/4 comma -2. Then I have 1/2 comma -1. Then I have 1 comma 0. Then I have 2 comma 1, and last but not least, 4 comma 2. So these are all of the ordered pairs that I have for my actual function. Let's go ahead and graph both of these on the the coordinate plane so we can see kind of what's happening. So first things first, I'm going to go ahead and I'm going to plot my inverse function. So I have -2 comma 1/4. That's going to be right about here. Then I have -1 comma 1/2. That's right about here. 0 comma 1, 1 comma 2, and 2 comma 4. And so this is going to be the graph of the inverse function 2 to the power of x. So I'm going to say y equals 2 to the power of x. Now let's go ahead and graph the actual function. So I have 1/4 -2. That's right about here. 1/2 -1. 1 comma 0. 2 comma 1. And 4 comma 2. And so this is going to be the graph y equals log base 2 of x. Okay, so now we have the function and its inverse on the same graph. Now let's go ahead and talk about the domain and the range of each, okay? So let's look at y equals 2 to the power of x first. So we're going to explore the inverse. So the inverse has a domain of, well, this is going to be all real numbers, right? Because we are going left forever, and we're also going up and to the right forever. So the domain of the inverse function here is going to be -infinity to +infinity. Okay, let's go ahead and talk about the range. Well, as you can see, we kind of have an asymptote right here where this graph is getting closer and closer and closer to the x-axis, but we're never quite touching the x-axis. So the range is going to be from 0 all the way up to +infinity. The asymptote, which I'm going to call the horizontal asymptote, because again, for this one, we have a horizontal asymptote on the x-axis. This is going to be the line y equals 0, otherwise known as the x-axis. And then last but not least, we just need to identify the y-intercept, which the y-intercept of the inverse function is going to be 0, comma 1. Now let's take a look at the actual function, y equals log base 2 of x. So for this function, the domain is, as you can see, we have kind of an asymptote situation going here at this line. So obviously our domain is kind of restricted here because we only have x values to the right of that y-axis. So the domain is going to be from 0 up to +infinity. And that makes sense, right? Because the range of the inverse was 0 to infinity. So that means the domain of the actual one is going to be 0 to infinity. Range is going to be whatever the domain was for the inverse function, which would be -infinity to +infinity. And as you can see, this is going down forever, and it's certainly going up to the right forever as well. This time, we don't have a horizontal asymptote, but we have a vertical asymptote, and this asymptote just so happens to be the y-axis. So this is going to be the line x equals 0, otherwise known as the y-axis. And then last but not least, we need to talk about the intercept. Now here, we don't have a y-intercept because this graph is never going to touch the y-axis, but we do have an x-intercept at the point 1, comma 0. So as you can see, everything is pretty much reversed, right? So when we're looking at inverse functions in comparison to actual functions, we just see that everything is kind of flip-flopped, and that's really ultimately what inverse is. All right, example number 5. Now we are going to be looking at translating y equals log base b of x. So describe how the graph of the function y equals log base 2 of x plus 1 compares to the graph of the parent function. Okay. Well, let's go ahead and figure out what we have going on here. So obviously, if I have y equals log base 2 of x plus 1, that is something that's very difficult to plug things into because there's not really an easy way for that to happen. Also, because we have the plus 1 on the outside, it makes things complicated. It's not as simple as just finding the inverse and then plugging in my x values, okay? This time, we're going to have to work a little bit harder. But what I want you to recognize is that y equals log base 2 of x plus 1, I could rewrite this a little bit so that I could create exponential form out of this logarithmic form. So what I could do is I could subtract 1 from both sides. Then I get y minus 1 equals log base 2 of x. And since my logarithm is now by itself, I can rewrite this logarithm into exponential form. So if I were to put this in exponential form, my base would be 2. I'm raising it to the stuff on the other side, so 2 to the y minus 1, and that is equal to x. So as you can see here, I could rewrite this logarithmic form into exponential form just by rearranging a couple of things. And now I have a situation where I could easily plug stuff in. Now, this is a little bit different than what we're used to, because what we're used to is we're used to having all of our x values as test points, and then we plug in our x values to the function. But this time, since y is kind of what's easiest to plug into here, I'm going to create test points for my y values, and I'm going to plug my y values into the exponential function to figure out what the x values are that correspond to that y value. So let's go ahead and plug all of these y values into the rearranged equation in exponential form. So first thing I'm going to plug in is -1 for y. So I have 2 to the power of -1 minus 1. That gives me 2 to the -2, which I can rewrite as 1 over 2 squared, or 1 over 4. So when y is -1, x has to equal 1 over 4. Next one, I'm going to plug in 0 for y. So I have 2 to the 0 minus 1. That's 2 to the -1, which I know I can make that positive by flipping the fraction bar. So I get 1 over 2. So when y is 0, x is 1 over 2. Now let's plug in 1. We have 2 to the 1 minus 1. That gives me 2 to the 0. Anything to the 0 power is 1. So my input is going to be 1 when my output is 1. Let's plug in 2. We have 2 to the 2 minus 1. That gives me 2 to the first. Anything to the first power is 2. So my input is going to be 2 when my output is 2. Last but not least, we are going to have 2 to the 3 minus 1. That gives me 2 squared. We know 2 squared gives me 4. So when my output is 3, my input is 4. Now I can go ahead and graph this on my coordinate plane. So let's go ahead and plot those points. My first point here is going to be 1/4 comma -1. So that's right about here. Then I have 1/2 comma 0. Then I have 1 comma 1, 2 comma 2, and 4 comma 3. I'm going to connect those dots using this smooth curve. Okay, so let's go ahead and look and see what happened here. Well, if I look at my graph up above, that was the graph of y equals log base 2 of x. This one right here was log base 2 of x plus 1. So what happened is, well, as you can see, let's look at specifically this point right here. We have the point 1 comma 0 on my original graph. And notice how when I'm down here, when I have plus 1, my point went up. So now I have the point 1 comma 1. So all that happened was I had a vertical shift of 1. So y equals log base 2 of x plus 1 has a vertical shift of 1. So I'm going to say this graph shifted. So I'm going to say this graph shifted the parent up 1. And that totally makes sense because that is kind of what we've been talking about with all of these different types of graphs. When we have a number being added on the outside, that's your vertical shift up or down. So since we have the plus 1 on the outside, that says, hey, we're going to take the original and we're going to shift it up 1 unit, and otherwise everything else is going to stay the same, but we just got to shift everything up 1. So that is going to be the difference between the parent graph and the translated graph. Very good. One more thing to note here is that the asymptote is still the y-axis, right? The graph, even though it moved up 1, is still never going to touch that y-axis. Okay, let's go ahead and move on to the last page, example number 6. So last but not least, we're going to talk about another example of translating. Describe how the graph of the function y equals log base 2 of x plus 1 compares to the graph of the parent function. So kind of the same thing, right? We're going to compare this to log base 2 of x on the other page, but this time we have x plus 1 in parentheses. You might have an idea of how this is going to work, but let's go ahead and illustrate it to you. So once again, I have y equals log base 2 of x plus 1. If I wanted to put this in exponential form to make my life a little bit easier, what I could do is I could say my base is 2. I'm raising it to the power of y, and that is equal to the inside stuff, which is x plus 1. So as you can see, I could easily subtract 1 from both sides, and then I would get x equals 2 to the y minus 1. So kind of a similar situation to the last example. It would be easier to plug in y values to this equation that we have rearranged a little bit. So I can plug in different test points for y's and figure out what my x values are. Let's go ahead and start by plugging -1 in to this function below. So I have 2 to the y minus 1, but this time I'm going to have 2 to the -1 minus 1. 2 to the -1 is 1 over 2. minus 1, and we know that 1/2 minus 1 is just negative 1/2. So when my output is negative 1, my input is negative 1/2. Now let's plug in 0. I have 2 to the 0 minus 1. Anything to the 0 is just 1, so I have 1 minus 1, and that gives me 0. So x is 0, y is 0. Next one, I'm going to plug in 1. I have 2 to the power of 1 minus 1. That gives me 2 minus 1, which is just 1. So my x value is 1. Now plug in 2. I have 2 squared minus 1. 2 squared is 4 minus 1, and that gives me 3. So x is 3, y is 2. Last but not least, 2 to the third power minus 1. 2 to the third power is 8 minus 1, and that's going to give me 7. So x is 7, y is 3. Let's go ahead and plot those points. We're going to go ahead and copy those down. So I have negative 1/2, negative 1. Plot that one first. 0, 0, 1, 1, 3, 2, and 7, comma 3. And this is going to be the graph of this logarithm. Okay. So let's go ahead and see what happened here. So when I have the graph y equals log base 2 of x plus 1, let's go ahead and compare this to the one on the other page. We're going to look at this one. So one of the points that I can look at here is I can say, hey, on this graph, I have the point, let's go ahead and look at one of the ones over here. I have the point negative 1/2, negative 1. But then, or actually that's positive 1/2, negative 1, my bad, that's positive 1/2, negative 1. But then on this graph, I have the point negative 1/2, negative 1. So literally all that happened is the graph that had the point here shifted 1 unit to the left over here. And that makes sense because we have x plus 1 inside of the parentheses. We know that that stuff inside of the parentheses gives us horizontal shifts, and we're thinking opposite. So x plus 1 is telling us, hey, we're going to move this to the left 1 single unit. So all that this graph has done is it's taken the parent graph and it said, hey, the graph will shift left 1. Now, when we shift left or right, this gets a little tricky because it also kind of messes with our asymptotes. So our asymptote for the original graph, right, was the y-axis. But since we shifted left 1, the asymptote is also going to shift left 1. So now our asymptote is the line x equals negative 1. So I'm going to say, okay, well now, since I shifted everything to the left, my vertical asymptote also shifted left. And now it's the line x equals negative 1. So I'm going to highlight that, showing that this is my new asymptote. All right, guys, so that is pretty much the deal with logarithms and some of the basics. We'll go ahead and explore these a little bit more later on. Thanks you guys so much for tuning in, and I will see you back here next time. Thank you.